we uh, we are now going to start our presentation. The title is very relevant nowadays. It's about the future of alternate fuels in cement industry. And the first question which comes to our mind is why alternate fuels? What is the purpose of alternate fuels? Why we want to put a lot of thrust on alternate fuels? If we see our dependence, like if we talk of in India, our dependence is mainly on coal, and in Middle East, it's mainly about crude and HFO, and with some countries, natural gas. So the main issue is that these are not renewable sources, so their stocks are getting depleted. So we need something to support that. So we need some alternate sources also, so that we can manage the situation. The next important point comes is greenhouse gas emissions. We know that all these natural resources, they are adding to our greenhouse gas emission, and our environment is getting impacted very heavily. That is the one reason where we want to reduce our dependence on primary fuels like coal, oil, or HFO. Third important point is energy security. Particularly, that is very relevant when our dependence is on imported fossil fuels. Like in many countries, if you know that during COVID, we saw this crisis when the whole economy got impacted because main fuels were imported, and then there was an issue of availability and foreign exchange. So everybody must have some security about the energy, because without energy, nothing is possible. The growth and everything is dependent on energy. So energy security also strengthens once we use alternate fuels. Then important thing is, if we use alternate fuels, we convert waste to energy. And solution to better waste management, ultimately we have to manage, if we have to use alternate fuel, we have to manage the waste in a better way. That will be the pre-requirement to use alternate fuel. So that also gets managed. Then we know that in major cities, we find large landfills are there, huge MSW stocks are lying there. So those landfills also can be reduced if we go for use of alternate fuels. And the final and the most important part is energy cost. So ultimately, use of alternate fuels impacts your cost. It reduces your cost of production. So today our agenda is basically we are focusing on Indian cement industry. So what is the AF journey? So the alternate fuels are there for 20, 30 years. People are using. So how in India vis-a-vis other countries, what is the journey for alternate fuels? Then what are the available alternate fuels and types in India? Then we will be looking at what are the impacts of AF usage. Then what are the technical advancements which we foresee in coming future with respect to pyro processing, co-processing systems in AF. Then what is the Holtec role for enhancing AF usage? And what are our global experience with respect to alternate fuel usage in pyrolysis process? So we'll present one or two case studies about the AF usage and Holtec role in that. So Indian cement industry AF journey. If we look at the growth of alternate fuels in India, in 2010, first time the CPCB guidelines came regarding co-processing, the AF usage was around 0.6% 2010. From 2010, it is increasing very gradually to 1.1, 3% in 2016, when the hazardous management rules came into existence. And then the use of hazardous waste also included in co-processing. Then in 20, it shifted from biomass, MSW, and other waste. So our usage was 4%. It increased very gradually to 23 in 6%. And in 25, we are expecting around 7% TSR. This is an overall number. And at 2030, our industry target is 25%. So if we see in last, say, 2010 to 25, so 15 years, the increase is just 7% from nearly 0 to 7%. But our target is now 25%. So the target looks quite huge. And there is both, the target looks tough, but at the same time, it poses a lot of opportunities for AF usage in the coming years. So maybe next 5 years, you will find a lot of boost on alternate fuels from every quarter. And we can see a lot of changes take place with respect to alternate fuel usage. So if we talk of major players in cement industry, where do they stand? So if we talk of Ambuja, ACC, most of the players are around 7, 10, 15, I mean, 2%, 9%. But their targets of everybody is around 25 to 35% in by 2030. So majorly, will development will take place now in next 5 years in the growth of AF usage. And all major players have also put their targets for increasing their AF usage in the coming years. So Indian cement industry AF journey. If we look at the growth of alternate fuels in India, in 2010, first time the CPCB guidelines came regarding co-processing, the AF usage was around 0.6% 2010. From 2010, it is increasing very gradually to 1.1, 3% in 2016, when the hazardous management rules came into existence. And then the use of hazardous waste also included in co-processing. Now, if we talk of 25%, then we foresee as the source of waste stream at 25%. If you see, the various sources will be MSW, plastic, hazardous waste, waste and liquid waste, biomass, paint, resin, carbon black, etc. So the major source is expected is only MSW and RDF, which is around 10%. You can say nearly 40% of the total alternate fuel usage is going to be MSW. So MSW will be playing a very important role in the coming years. And as we can see around us, there is a huge stocks of MSW lying and which need to be depleted in the coming years. Now, if we talk of 25%, then we foresee as the, if you look at overall country situation, we have over 170,000 TPD generation of raw solid waste. Out of that, typically 20 to 23% can be generated into treated MSW or RDF. This is what the potential is, around 35,000 tons per day. So if you see the breakup, normally organic waste constitute 50 to 60%, and the paper, cardboard, plastic, and other which is usable as a fuel, which works around 20 to 23%. And glass, metal, other materials are just has to be removed from the MSW. And if we see the distribution of cluster-wise where the cement is there, so we find Maharashtra, Tamil Nadu, Gujarat, and UP, Chhattisgarh area. So these are the major source of MSW which will be serving in future. Will provide the basic raw material like MSW, and which may be close to the cement clusters. If you look at overall country situation, we have over 170,000 TPD generation of raw solid. Now, what 25% TSR means? TSR, I understand that this is basically the thermal substitution rate in terms of heat. So if you say 25% TSR, what we mean is the overall saving in cost of production, say around 175 to 200 rupees per ton. And if we talk of uh, other components, one is if we continue business as usual, I mean, we don't take any effort on AFR, maybe our coal consumption will end up at 51.38 million tons per annum. So if we go for AFR 25%, it will get reduced to 38.53, around 25% reduction in coal consumption. And if we talk of carbon emission, we are again end up reducing by 25% from 123 to 92 million tons of CO2. Similarly, landfill area also will get reduced from 49.6 to 39.68 thousand hectares. So this is broad impact of AF if we are able to achieve 25% by 2030. Now, when we talk of alternate fuels, we are ultimately going for the decarbonization. So that is the long-term goal for for the whole planet, how to decarbonize. So we have taken, we are providing some decarbonization levers. If we talk of 670 is the current level, we can go up to 486 if there are following measures which can be done. One is energy efficiency. The potential is 2.5 to 3%. As you know, the Indian cement industry, fuel and power consumption wise, it's in a very good position if you compare internationally. The next factor lies is clinker reduction, clinker factor reduction. That has got a potential of 10 to 21%. And the AF fuel switching to alternate fuel, that has got a potential of 21 to 24%, which is a very good potential. WHR 5 to 7%, renewable energy 10 to 12%, and transportation shifting to electrical and all is 1 to 3%. By all these levers, we can bring our CO2 level by around 25 to 27%, rather 670 to 486. Now, when we talk of India, we get interested what is the global scenario. So if we see, we are giving you details about various countries. If you see the right side, it's mainly the European countries where the levels are in Austria, Germany, Netherlands, they are 68, 71, 76. And if you talk of Europe, around 46% is the average EU level. And then if you talk of India, we are nearly at the bottom of the table, which is around 7%, along with China, around 8%. The average, world average, you can say around 18%. So this is basically, we can say there is a, if we are at a very low level, the potential is very huge. We can go to much higher level as we have improved in our power consumption, fuel consumption figure. The AF consumption level also has a potential which has to be exploited in the coming years. Now we have summarized a few reasons which why, because this question is very pertinent, why we are lagging behind the European Western countries. One is, of course, regulatory and policy framework. Western countries, they are very stringent norms and their enforcement is also very strong and compliance is very effective. Whereas in Indian condition, policies are obviously there, but regulatory framework enforcement mechanisms are still evolving and compliance is weaker and less stringent. So there are some economic consideration, of course. As we know, the Western countries, their their cost is going up because they're putting a lot of environment tax to discourage use of fossil fuels. But at the same time, they're incentivizing alternate fuels that to reduce the cost and that also offset some of the initial investment. Whereas in Indian context, if you see our because coal is our main source of fuel and it is available within country, so our cost of fuel is much lower comparatively, and financial incentives are relatively very limited. So initial investment and the fluctuating availability is causing major problem in increase because the investment we need investment if you have to go to high levels, and if that is not there, then availability is also fluctuating. So that is also a deterrence. Then waste management and supply chain. European countries or even whole Western world, we see their waste management system are well placed. They have well structured infrastructure, and there is a proper separation system and processing units, which is providing ready-to-use alternate fuels to the cement plant. Here, the situation is not like that. Here, waste management infrastructure is still underdeveloped. Collection, sorting, processing of waste is inefficient, and it is leading to inconsistent supply of alternate fuels. So, supply availability and all are really a constraint till our infrastructure gets improved. Now, another is technological infrastructure. So better technological infrastructure is essentially the equipment, how we are equipped to handle AF, which requires specialized system for storage, pre-processing, and combustion. And in Western countries, the R&D is quite impressive. They have put a lot of investment in R&D and improving the alternate fuel technologies. Where in Indian context, we still lack in infrastructure to handle the specific requirement. We still struggle with the moisture, particle size, and contamination. So all these these problems are creating issues in increasing the use. And upgrading the infrastructure is causing is need investment. So we find that small players, they find difficult to invest in this developing infrastructure because their cost will be high if we go for higher alternate fuels. So that is another hindrance. Now, if we talk of other things, we cannot have control because a lot of things are related with the government policies and plans. But we can talk of infrastructure gaps for achieving 25% TSR. Holtec has been studying this, going to various plants and studying what are the available infrastructure, what are the various issues. So we find that pre-processing plants to condition RDF and other fuels which are suitable to kill requirement are very limiting. There are very limited number of pre-processing units. Alternate fuel storage and advanced fuel feeding system. This is mainly related to the infrastructure within the plant. So those are very limited, but now it is also growing. So many plants are investing now in developing the storage, proper storage, advanced feeding system, and handling facility for all the fuels. So this is a upcoming thing which we find that of late we are finding that people are going ahead with this kind of investment. Then bypass system, as we know that in India, bypass systems are not available because we don't have our raw material like that, except in Gujarat, few plants in Kutch region. The rest of the country, there is hardly any bypass system available. So all this has to be installed if we talk of our AFR usage. That calls for investment. Then fuel handling and firing system. Of course, we are mainly dependent on coal and solid material feeding. So we are our burner system feeding system are available with that facility only. Then we find a lot of pyro system capacity bottlenecks. Again, it depends on plant to plant. Somewhere pre-calciner capacities, fan capacities, kill inlet areas, bag house. So all these things, there are a lot of places we find bottlenecks which doesn't allow to go beyond certain limits, the AFTSR percentages. Similarly, DNOx and DSOS systems are very limited, which are required to comply with the environment norms. And then automation system, of course, we need to install with when we go for higher system because the proper uniform material, consistently blended material, and a constant feed is most important for sustained AFR usage without affecting our plant performance. So these are broad technological infrastructure gaps we find, and these are have to be taken care of. Now, if we talk of alternate fuels in Indian context, we find agriculture biomass, this rice husk, wheat straw, corn straw, sugarcane bagasse. So some of the issues, some of them have some issues like chloride, where in some cases ash content is high, but they are all used as alternate fuels suitable for pre-processing and co-processing of as alternate fuel. Non-agriculture biomass is another type of fuel, which is dewatered sewage sludge, paper sludge, sawdust. But in these cases, moistures are really high. And then in some cases, heavy metal and chlorides are also on the higher level. Then we have hazardous waste, pollution, petroleum based waste. There we have the issue of dioxin and heavy metals, which can cause problems. We need to have a solution for that. Then other waste include MSW, waste oil, textile, and automatic shredder. So these are essentially the alternate fuels which are being used in industry. Now, what is the major impact of AF usage? We find that AF, of course, it all depends on which AF we are using, but we are giving a general thing. Again, we'll have to study for each AF what is the composition of AF and how much percentage is being used. So we have to define, we have to assess the system accordingly. But broadly, we find that chlorine bypass requirement comes with higher AF usage. It has a negative impact on specific heat consumption. It impacts negatively on production, mainly due to fan capacity limitation, calciner sizing. Then we have impact on clinker quality in many cases and environment impact emission also. It can impact. It has an impact on raw mix design in many cases. If specifically if alternate fuel has high ash or a high volatile component, then we need to optimize raw mix. Then there is a presence of if there is a presence of heavy metal, then that also can impact it. That need to be checked whether it should not cross the limits. Then there is another impact is in if we have an existing WHR already installed, and if we go increase our alternate fuel usage, then it may have positive impact on the WHR generation. But that becomes a problem because our WHR is designed for a particular gas flow, and we find that flows have gone up, so higher heat availability is there. So that also many times we need to study whether we can do something to improve the WHR potential. So these are broad impacts of AF usages. When we talk of technology, so basically we have to see what are the technological advancements coming up now. And this is mainly we when we talk of going for 25% TSR or higher. So if we talk of MSW, we find that we will see that there are basically two component MSW. One is normally provided within a plant, which is shown in the boundary limit within the plant boundary, and rest of the things have to be provided at the site where MSW or waste is collected. So that includes basically the process include MSW unloading, storage, inspection, and then primary size reduction. So we have to reduce up to say 200, 300 size at there only. Then some basic separation like ferrous fraction, then some inert material, and then glass, ceramic, stones. So all these things have to be separated there only, and then it is transported to the plant for further size reduction, say up to less than 75 mm, and converting into fluff if we have if that is available in the plant. So this is how the whole process goes. And if we see the typical flow sheet, we can see on the shredder that is the co-processing, that is pre-processing part, which require we put our received from the site or MSW, partly process you can say, and then we put into shredder, and from shredder we after magnetic separator it is screened. So 75 or less than that part is separated and it's stored for further feeding into pyro process. And the upper portion we have shown is feeding of that material into belt conveyor through extractor. It passes through the various belt conveyors and goes to the calciner through vibro feeder, double electric double airlock system, so that all cell integration is minimum. So this is a typical flow sheet for feeding and pre-processing of air inside the plant. And if you see the picture, this left side is feeding system where all the waste is being fed into the shredder, and right side is the shredder inside view. Now when we talk of higher alternate fuel usage, then few technologies which are coming up and they are available in the market, but in Indian context so far not much is seen because in India average level is still 7%, and some of the players which we are striving for bigger size. So that time they may be we are be forced to get in these type of technology. So one is pyro rotor. So these are basically we fire all the alternate fuel outside the calciner in a vessel which is rotating with use of tertiary air only. It falls into the system and nothing comes out. Everything goes into the calciner, but firing and all takes outside, and it provides the additional retention time, which is good enough to complete combustion of material. Generally, it is useful even for the whole tire chips, big size material, coarse material. Because if we find in Indian context, we get generally the material available is bigger size, coarse material. Our pre-processing is not that great, so these system will take care of that. It will give you adequate residence time for complete combustion and very good for waste and extremely poor burning property materials. Another index line, which is still it's available since very long. It's a hot disk, which is again for a high TSR rate, and we have facility for using Holtec bigger size material and lumpy material. So it does not impact our core process, that is the pyro process, and gives minimum hindrance in the main process, and our disturbances get reduced. Another option available in this case is a step combustor. So this is a relatively standard, a fixed type of system, which also increase the residence time or for the combustion of mainly fuel, which takes more time for to get convert into a fuel heat. So these materials are fired in this system, but this particular thing is has some limitations. So it can go up to 25% comfortably. But if we talk of higher size, 30, 40, 50%, then we need to go for other options. Now, when we talk of higher alternate fuel usage, then few technologies which are coming up and they are available in the market. Now, one important point in this thing is that Calciner also plays major important role in this. So most of the places you find the Calciner is not suitable for higher capacity, higher AF usage. So Holtec has done at many places, which is one of the case we have modified the Calciner, which capacity of Calciner, the residence time has to go up at least 5 seconds minimum. So that we have, if no option is available, at least we have to take the Calciner, put up a new Calciner completely, take out the duct, and then again back into the system, independently supported system. So this is important modification, which is required when we talk of higher AF feeding, higher percentage TSR. Similarly, this is another drawing. This is another proposal where we have shown new calciner plus Pyro rotor together installed along with the modified TA duct and bottom cyclone. So this makes a complete modification of the entire Pyro bottom area. So these type of modification will be required when we go for higher thermal substitution of alternate fuel. So when we talk of Holtec role, we play both our role, our goal. I mean, both our role is there. Conceptual. First part is conceptualization, and second part is execution. So we are carrying out feasibility study, which involves AF evaluation and impact assessment, evaluation of whatever identified alternate fuel. We need to assess those fuel, its impact on system, its impact on clinker production, product quality, emission, pyro equipment performance, and stability at different level of TSR. So at different TSR, we estimate what will be the impact, what is impact on the system and on product quality, quantity, and heat consumption. Then we estimate raw mix, what are the changes required for AF with enhanced AF usage and the compatibility of existing system. With increasing AF, our system bottlenecks get exposed. So we have to find out what are the bottlenecks and what are the modifications required. And because we always have various solutions to de-bottleneck our system, we need to take a decision, and that needs a capex estimation for each modification or each level of substitution. And then we work out simple payback so that it's easy to take a decision whether we want to go for to what level we want to go for substitution. So this becomes a conceptual part. And then next becomes once decision is formed by management, then execution comes into play. Then our role starts with basic engineering, procurement services, detailed project engineering, equipment inspection, and site supervision. So that becomes an execution part, and we are playing major role in this. So in the past, we have executed 50 completed projects, which also include studies and actual execution of the project. Now we come to the case study. Recently, we have completed one cement plant upgradation or modification in Europe, one of the plant in Europe, where the existing capacity of the plant was it's a 5-stage treater plant, and 4,500 was the capacity. And TSR already running TSR 38%, which majorly it was fed into main burner. Calciner was 6%. And main reason is the calciner size, residence time was very small. It's 2.5 seconds. So they were not able to push more far in the calciner. And further, cooler were also old generation coolers. So there was a lot of heat possibility for modification for increasing the heat consumption in cooler. So this is a plant in Europe, and these were the main alternate fuels. Main traditional fuel was of course coal, and alternate was animal meal, seeds, solid recoverable fuel, fluff, sawdust. So the management target was to enhance the capacity marginally by 4,500 to 4,850. But major thrust was to enhance alternate fuel. Overall, TSM target was 80%, with 90% replacement in calciner fuel. So majorly, we are supposed to replace complete fuel in calciner with alternate fuel. Of course, overall operational efficiency improvement and reliability improvement. So the major modifications which were done was top cyclone replacement, a new complete calciner which has a residence time of more than 8 seconds. Kiln inlet and tertiary air duct also was modified. And of course, an ID fan with higher capacity was installed to take care of additional volumes. And if you see the diagram, the new calciner is outside the existing pleater building and top stage, and then bottom stage cyclone also was modified accordingly, along with new inline calciner. Then there was a replacement of cooler, new generation cooler was installed, and the process filter were also extended for kiln and main back filter was also extended. The capacity was increased, and with cooler, hot hood was also modified accordingly. Original hood was very small. And then, of course, new AF storage handling dosing feeding system for calciner was put up for increasing from 32 to 80%. They already was operating chloride bypass, so that chloride bypass was because the capacity of bypass or the percentage bypass was going to increase with 80% bypass. So that modification was done to enhance the capacity of existing chloride bypass. Now, key aspect which were considered here, there were a few interesting things. One is that here, because this plant, they were getting pre-processed fuel already from some source outside the plant. So pre-processing activity was not done inside the plant. So the AF reduction was, the size reduction was 1 to 2 mm, and homogenizely prepared alternate fuel was considered, was taken up to the plant site. Then chloride bypass, if we talk, of course, the bypass was extended, but the gases, there was no separate vent was provided. All the bypass gases were fed into cooler recuperation zone after static grade. So the cooler vent gases were going into the cooler. So there is no separate vent for because there are certain norms in EU for that. So that was a different. I mean that's a concept which was followed. And of course, bypass dust was used for cement, added into cement later on. And similarly, the storage, alternate fuel storage sheds vent gas, which is many times it is vented in air. Here, all those gases were taken and put into the cooler area, which was first fan only, that quench air fan. So that was used for quenching. And so that also minimizes the foul smell issues, which are very common in such AFR feeding area. So that all the foul air was fed into cooler. Plus NOx and SOx, there was SNCR and hydrated lime injection system was already provided there. So finally, after complete completion of the project, clinker production target achieved was 5,000 TPD clinker against 484,850. And there was reduction in heat consumption, primarily due to capacity increase and new cooler, more efficient cooler. Overall TSR achieved was 81%, and calciner TSR replacement was 99%. And cooler of thermal efficiency, of course, it has increased to 75%. So this was the case in Europe where substitution rate was very high. And of course, one contribution is very good pre-processed fuel, which which was available there, that has been used with a proper pre-processing unit or with proper co-processing unit with all the desired modification taken to take care of such a high substitution. And it was successfully completed. Now, cement plant, this is another example of some cement plant in India where where the TSR has to be increased to 35%. So these were the main alternate fuel, which is mainly RDF and some other biomass and organic waste. So majorly it is 29.8% was RDF out of 35%. That was the target. Plant capacity 8,000 TPD, thermal substitution rate already 20% was there, was already operating. Heat consumption 741, and chloride content in hot meal was 0.44, which was well within the range. So no bypass requirement was there. And calciner was adequately sized, 14 seconds. From this operating condition, now we had to go for 35% by TSR. So we studied the impact. What will be the impact of 35%? We estimated that heat consumption is expected to increase by 23 kilocalorie because of high moisture of 40% in RDF. Product impact, production was impacted around 1,000 ton reduction in TPD, 1,000 ton per day reduction in clinker capacity if we don't take modification in the system. So this was the expected reduction, which was quite significant. Bypass reduction requirement worked out now with 4% chloride bypass, because previously with 30%, 20%, there was no requirement. Now we required 4% chlorine bypass. And we propose a 12% design, because in case they go for further increase in capacity in feeding AF usage, maybe that will also be used. So provision was kept for high. So our major proposal was to go for a new preheater fan, the replacement of top stage cyclone. That also helped in reducing pressure drop, return dust reduction to 4 to 6%, and then so overall saving of 6 to 8 kilocalorie because of this modification. And then tertiary air modification, enlargement of tertiary air from 2.9 to 3.5. Or it was the idea was that even we can go for parallel TAD. So the result was that we achieved some 35% TSR, and the production loss was averted because we took some major the required modification. And it was achieved 35% TSR.